students, let's discuss about how actually HCl is estimated using potentiometric titration today. Now this potentiometric titration involves the study of EMF values during the course of acid-base titration. So when you measure the potential difference values during the acid-base titration, the changes that are occurring in the potential difference indicates the completion of the acid-base titration, from which we derive the reaction completion and the concentration calculation and the amount of HCl finally. So this is how we approach with the potentiometric titrations. Okay. So let's start with the principle of the reaction. How actually the principle helps out in understanding the whole experiment and the estimation part. So principle involves the use of two half cells. Usually any electrochemical cell involves the use of two half cell reactions. One is going to be the oxidation half cell and the other one is going to be the reduction half cell. Now let's talk about the oxidation half cell. Now oxidation half cell involves the release of electrons and the reduction half cell involves the acceptance of electrons. So this particular reduction reaction and oxidation reactions takes place in an electrochemical cell, and this migration of the electrons and the movement of ions can be possible in a smoother way, that is accumulation of charges can be prevented by using a salt bridge during the electrochemical cell reaction. So that is represented with double line. Okay. So this is the complete cell notation, and in this particular estimation of HCl, we are going to use two electrode forms. One is going to be the saturated calomel electrode and the other one is going to be the quinhydrone electrode. With the help of quinhydrone electrode and saturated calomel electrode, we will be using the potentiometer connected with these two electrodes to read out the values of the potential difference of the cell, and with the changes that are occurring with the potential difference values, we will be able to know where exactly the acid and base have completed their reaction, that is neutralization. So this endpoint study is made with the help of the potential difference values without using an indicator. Okay. So when you are using this particular electrode, that is the calomel electrode, it acts as a reference electrode, or it is otherwise called as a secondary standard electrode whose potentials are constant. So its potential, as we are using saturated KCl solution, the potential of this particular calomel electrode is going to be 0.2422 volts. And this is going to remain unchanged throughout the electrochemical process. Now the other electrode that we are going to use, that is the other half cell, the reduction half cell, we have the construction of the quinhydrone electrode. Now this quinhydrone electrode acts as the indicator electrode. Now what is the indicator electrode here? You have the 1:1 proportion of quinone and quinol, okay, which is taken along with the solution of HCl. So 1:1 proportion of quinone and quinol forms quinhydrone, and this quinhydrone is in the black powdery form, which is added to the solution of HCl, which we are going to estimate. And this quinone and quinol, okay, in 1:1 proportion is commonly called as quinhydrone. And this quinhydrone, when added along with HCl solution and placed along with the platinum electrode, forms the quinhydrone electrode. And this quinhydrone electrode is sensitive to the H+ ion concentration. Okay, so that's why we call it as an indicator electrode, because it is subjected to change with its potential with the change in concentration of H+ ions in the solution. Okay. Now this particular electrochemical cell involves oxidation reaction and reduction reaction. Now the oxidation reaction which occurs at the calomel electrode involves the oxidation of mercury to mercurous chloride, and every oxidation reaction is involving the release of electrons. Okay, so there is a release of 2 electrons with the oxidation of mercury to mercurous chloride, and this mercurous chloride is commonly called as calomel. Okay, and that's why we call it as a calomel electrode. Now this reaction, that is the oxidation process, which releases the 2 electrons, are utilized during the reduction process. Now what is a reaction at the reduction end? The quinone which is present with the quinhydrone is getting reduced to quinol, and this particular reduction depends upon the availability of H plus ions. Now in our experiment, these H plus ions are coming from the HCl solution, which on dissociation forms H plus and Cl minus ions. So availability of this H plus ions from the solution are going to decide over the reduction reaction. As long as we have the availability of H plus ions with the solution, the reduction of quinone occurs towards the quinol. So the forward reaction occurs as long as we have the hydrogen ions coming from HCl solution. And these 2 electrons which are coming from the oxidation end are utilized at the reduction reaction. So quinone is getting reduced to quinol in the reduction half cell reaction. Okay. Now if you look at the overall cell reaction, mercury is undergoing oxidation to form mercurous chloride, and quinone is getting reduced by utilizing H plus ions coming from HCl to form quinol. So this is the overall cell reaction. Okay. Now this particular reaction, where the potentials of the quinhydrone vary with respect to the availability of H plus ions, is the main criteria where we find the change in the overall EMF of the cell. The EMF of the cell are displayed over the potentiometer. So we keep on reading the values of EMF during the course of an acid-base titration, and depending upon the variation in the values of the titration, E cell values, we find the endpoint of the reaction. So it is mainly the concentration of H plus ions during the course of titration. We find the variation in the E cell values. From the E cell, we derive the concentration of the H plus ions. Okay. So we have the E cell values that are obtained on the potentiometer during the course of the titration, that is base against the acid. We observe that there is difference in the values of E cell occurring. Now what is this E cell actually? The difference between the reduction potentials on the right hand side minus left hand side electrode. Now when you consider the right hand side electrode, this is quinhydrone electrode, whose potential is considered to be E naught minus 0.0592 pH. Now this pH is nothing but the negative logarithm of H plus ion concentration. So H plus ion concentration will decide over the electrode potentials of the quinhydrone electrode. Now on the right hand side, on the left hand side, we have the saturated calomel electrode. Now this potential of saturated calomel electrode is going to remain constant, that is 0.2422 volts. Now when we overall observe the changes in the values of E cell during the course of acid-base titration, that is HCl against the sodium hydroxide that we are taking, we observe that there is decrease in the values of E cell. That is because when base is added to the acid, there is continuous addition of OH minus ions which are neutralizing the H plus ions in the HCl solution. As we already discussed, the reduction potentials of the quinhydrone electrode depends upon the H plus ion concentration. The H plus ion concentration whenever decreases, the potentials of the quinhydrone electrode also decrease. Now when you observe the overall cell EMF of the reactions, that is whenever you are adding base to the acid, there is continuous decrease in the values of E cell during the course of titration. This decrease is attributed to the decrease in the values of the potentials on the right hand side electrode due to decrease in the concentration of H plus ions on addition of base. So overall EMF of the cell, when you observe with the reaction electrochemical cell, it is 0.4574 minus 0.0591 pH. Okay. Now whenever you are adding this NaOH to the HCl solution, there's going to be continuous decrease in the values of the potential values, and from positive EMF values they tend to decrease to negative EMF values. Now you observe this whenever you are adding the base to the acid in 1 ml lots. Okay, from the potentiometer you keep on observing the changes in the values of EMF and plot the graph to obtain the results. Now during the titration, you keep adding sodium hydroxide in 1 ml lots and continuously monitor the EMF values. Now you find that there is a continuous decline in the value of EMF with the volume of NaOH added. These are the cell EMF values. So, as long as you have the H plus ions available in the solution of HCl, the potential values are in positive range. Now on completion of the reaction, that is on neutralization, on continuous addition of NaOH further, suddenly the values of EMF fall from positive to negative EMF values. So this particular fall of the potentials from positive to negative will indicate the completion of the reaction. So this is how we are able to read out the endpoint of the reaction. Now apart from this particular titration, to have a close watch on how the endpoint is, where exactly is the endpoint occurring, we again do the whole titration plotting the differential graph. For plotting of the differential graph, to have a more accurate reading of the endpoint of the reaction. So for which we will add 0.2 mL near the endpoint of the reaction and obtain the graph taking delta E by delta V values. That is difference between the EMF values, two EMF values, consecutive EMF values, and the two consecutive volumes. So we will be taking in 0.2 mL near the endpoint of the reaction and obtain the graph taking the delta E by delta V values, which gives you the volume of NaOH that is utilized at the point of neutralization. Exactly from the graph it is derived, and this is read out as V2 dash. Okay, so once this V2 dash is derived, we can derive the concentration of HCl using the law of equivalence, that is N2 V2 is equal to N3 V2. This is pertaining to sodium hydroxide and this is pertaining to HCl. As we already have the standard solution of NaOH used, we know the normality and the volume of NaOH will be derived from the graph, and hence we will try to find out the concentration of the HCl solution, as you already know the volume of HCl taken during the experiment. Okay. To start with the procedure in the estimation of HCl by potentiometry, we started with preparation of standard oxalic acid solution. Okay. Now how to prepare a standard solution? We have the sample of oxalic acid, okay, and this is to be weighed, and then we check out W1 and W2, and then finally obtain the weight that is transferred into the standard flask, and then we make up the solution to 100 ml, and with the help of this normality equation, weight by gram equivalent weight into 1000 by volume in ml, we will be able to find out the concentration of the primary standard solution, that is of oxalic acid. Now we will just check out with the procedure. Now this is the weighing balance which I have, and I am weighing the salt of oxalic acid. Now the weight of the salt is about 5.66 grams. Okay, I weigh the weighing bottle along with this oxalic acid, and then I am transferring the salt into the standard flask, and then I have to check the weight of the empty weighing bottle there. This is about 4.37 grams. Okay, so now what do I have over here is the difference between 5.66 and 4.37 grams, that is W1 minus W2. So let me do the difference. This is 1.29 grams which is transferred into the standard flask. Now let's see how to prepare the standard solution. This is 1.29 grams which has gone into the standard flask. Now I am preparing the standard solution of oxalic acid. Now this is the standard flask, and I am collecting all that salt adhering to the sides of the container and preparing a uniform solution. So shake it thoroughly with adequate amount of water, distilled water, and once it gets totally dissolved, you have to add the rest of the water until the mark. So this is exactly 100 ml of the solution of oxalic acid which we have prepared. Now shake it thoroughly to use it for further procedure. That is, in part B we will be using the standard solution. So students, let's start with part B, that is after the completion of preparation of standard solution. That standard solution is used in standardizing sodium hydroxide, which is considered to be the secondary standard solution or link solution. Now for that, what you need to do is, you are taking about 20 ml of standard oxalic acid. Okay, so let's pipette out 20 ml of standard oxalic acid. Now I have this pipette. I am using the standard solution. So let me run the solution into the conical flask. I am taking this solution into the conical flask. Now during standardization of sodium hydroxide, we are using the indicator phenolphthalein. I am going to add just about 2 to 3 drops of indicator, and then this burette is filled with sodium hydroxide. Now I titrate it against the solution of sodium hydroxide till the color changes to pale pink. You can run down the solution slightly faster initially. Once you find the change in the color, slow down the burette. And the color has to be pale pink. Okay, now once you attain this pale pink coloration, note down the volume of the solution used up till the end point from the burette. This is about, say, 22 ml. Initial volume is 0 and the volume used up till the end point is 22 ml. Net volume is going to be 22 minus 0, so it is 22 ml. Now what you need to do is repeat the titration until you get the concurrent values. So once you get the concurrent values, say it is again 22 as the second titer value as well. Okay, so note down the readings accordingly. So suppose if it is 22 ml again, so you consider this volume exactly at 22 ml, which is used up for neutralization. Now what are, so to calculate the concentration of sodium hydroxide, we are taking the help of the normality and volume of oxalic acid and the volume of NaOH that is used up. Okay. So using the law of equivalence, we have the derivation for N2, that is the normality of NaOH as N1 V1 is by V2. So this is N1, which is 0.2047 into V1, which is 20 ml. Volume of oxalic acid used is 20 ml by 22 ml is the volume of the NaOH from the burette. So calculate and find out the normality of sodium hydroxide. Now let me check the value. This is about 0.1, I guess it is 0.18. It's 0.1860 normal. Okay. So this is going to be the normality of NaOH, which is to be used again for estimation part. So this particular normality value is going to be very crucial for the estimation part as well. Okay. So we have derived the normality of NaOH, which will be used for estimation further. Now let's see with the estimation part. So students, let's start with the estimation part of HCl using the potentiometer. I have the potentiometer which are connected to two electrodes. You have two terminals connecting the two electrodes. One is the platinum electrode. I have dipped it in 20 ml of HCl, and the other electrode, which is calomel electrode, which is considered to be the reference electrode, it's dipped in saturated KCl solution. Now, what do I do is, I need to add a pinch of quinhydrone to this. Now let's add a pinch of quinhydrone. This is 1:1 proportion of quinone and hydroquinone. I just stir it properly and then place it, and then so this is the reduction half cell platinum along with HCl solution with quinhydrone, and the other half cell is calomel electrode dipped in the solution of saturated KCl solution. Now in order to obtain the proper result from the potentiometer, I am placing the salt bridge connecting both the half cells. Okay, and this is a salt bridge. You can see the U-shaped glass tube, okay, filled with agar-agar and KCl along with ammonium nitrate. Okay, so this is placed over here, and then I have the burette which is filled with sodium hydroxide. Now I perform the acid-base titration to find out the endpoint of the reaction. Now let me start. This is the whole setup. So when I check the potentiometer, I find the initial reading to be 378. Okay, so let me note it on my tabular column with 0 ml. It is 378 millivolts. Okay, now I start with the titration. I am taking 1 ml lots of NaOH into HCl. Okay, now let me stir the solution for uniform availability of sodium hydroxide in HCl. And when I check the solution, when I check the EMF values, it has dropped down to 374. So with 1 ml of NaOH added, the value is 374. Similarly, I'm going to note down with the rest of the addition of sodium hydroxide volumes. So students, we have continuously performed the titration as shown, as per the procedure shown, and we found that there is a continuous drop in the values of cell EMF, and this is attributed to the neutralization of H+ ions in the solution due to addition of NaOH, and you can see there is a sudden fall in the values of EMF to negative. Now this negative value indicates the completion of the reaction. Okay, so positive to negative drop down of the EMF values is showing the completion of the neutralization. There lies the point of influx. Okay, and I have further taken a few more values after this point of influx to obtain a standard curve. Okay, now this gives me a rough idea about where exactly is the point of neutralization occurring. It's occurring between 9 to 10 ml. Now where in between 9 to 10 ml? It could be at 9.1, 9.2, 9.4 and so on. So to get more accuracy with the volume of NaOH utilized for point of neutralization, I perform a trial 2. Now this is how I take the values for trial 2. Now nearing the endpoints, I focus more with the closer volumes added. Okay, so you can see that from 8 ml onwards, I have taken 0.2 mLs. Okay, and then from here on, when I added 0.2 mLs, I recorded the values of EMF accordingly. And again I found that the negative value has occurred at 9.4 ml. So this influx, that is from between 9.2 to 9.4, is observed here. So you have got a better closer value. Now I have obtained the delta E values from this particular reading or observation. I have obtained the delta E values. Now what are these delta E values? Difference between the two consecutive EMF readings. Okay. Now apart from delta E values, I have obtained the values of delta E by delta V as well. What is delta V? I consider this closer values mainly. I am mainly focusing on these 0.2 mLs. So difference between this point to another point is 0.2 volume, right? So I am focusing on delta E values with 0.2 ml addition of NaOH, and I obtain the values of delta E by delta V in this way. Okay. So delta E by 0.2 gives me this value of delta E by delta V. You can see that at this particular point, okay, at 9.4, I got the peak value 1055. Got it? This is where the point of influx is lying. So I plot the graphs with both the trials of observations obtained. Okay, the first trial gives me an integral graph which shows a rough value where between 9 and 10 ml I got the point of influx. Okay, that is the drop down of the EMF values from positive to negative. And the second trial, you can see that the peak is obtained over here at 9.4 ml. Got it, students? So at 9.4 ml, I get the complete point of neutralization. That's what it says. Okay. So volume of NaOH that is required for neutralizing your 20 volumes of HCl taken is 9.4 ml. So accordingly, I have to calculate N2 into 9.4 is equal to N3 into 20 ml, because we take 20 ml of HCl. Okay. So I calculate the normality of HCl and then obtain the amount of HCl. Now weight by gram equivalent weight into volume is given as normality. So normality into its gram equivalent weight gives me the amount of HCl. Okay. So this is how I calculate the normality of HCl and then obtain the amount. N3 into 36.5 is its gram equivalent weight of HCl, and so I obtain the value of amount of HCl in grams per liter. So this is how we need to complete the reaction. Okay. Thank you. Hello students. Now let's discuss about the estimation of iron by potentiometric titration, and here this is going to be a kind of redox titration where we'll be performing a titration between ferrous solution and permanganate solution, and availing or by deriving the values of potential difference during the titration, we'll be able to draw the conclusions, that is finding out the concentration of ferrous ions and then amount of ferrous present in the given solution. Okay, so let's start with the principle involved in this particular reaction. Now in order to find out the amount of ferrous present in the given solution, we'll find the EMF values of the cell, okay, during the performance of the redox titration between the ferrous ions and the added potassium permanganate. Learning the variation in the cell EMF values, we'll be able to know again where the redox titration is complete, and from the values obtained by using a graphical representation, we'll be able to find out the amount of ferrous in the given solution. Now let's start how we find this whole scenario. First, let's discuss about how we construct the cell, the electrochemical cell for this particular reaction. Now we are using again two electrodes over here. Two half cells are involved. One is going to be the reference electrode, that is the calomel electrode, which is having saturated KCl. So it is going to be a saturated calomel electrode used as the reference electrode, which has a standard potential of 0.2422 volts. Now the other electrode that is involved is going to be the ferric ferrous electrode with platinum taken. Now this ferric ferrous electrode is actually built when you are taking the solution of ferrous in a beaker, and then by adding few drops of KMnO4 solution into the ferrous solution, you will be able to create an equilibrium between the ferrous and ferric ions. So this creation of the equilibrium between the ferric and ferrous ions creates the ferric ferrous electrode. This is the type of redox electrode that is built, and to bring about electrical contact with the external circuit, we are using the platinum electrode. Okay, so this is the whole cell notation, and as usual we'll be having a YouTube kind of the glass structure, which is called as the salt bridge, okay, which helps out in continuous flow of the charges, okay, to prevent the accumulation of charges. Now this particular electrochemical cell involves the following reactions again. As I told you, the left hand side electrode is going to be the anode and the right hand side electrode is going to be the cathode. The reactions at the anode are going to be again the oxidation of mercury to mercurous chloride, releasing electrons during the oxidation, and at cathode we find that there is continuous reduction that is taking place. The reduction occurs with ferric ions present to ferrous ions. So this is going to be the reduction, which is going to be possible with the release of electrons from the oxidation reaction. Okay. Now variation of the electrode potential at the ferric ferrous electrode depends upon the concentration of ferrous ions and ferric ions. So the electrode potential of ferric ferrous electrode with respect to the ionic concentration is observed. So we get the changes in the values of potentials with the ongoing titration of ferrous solution against the KMnO4. So observing these values of changes in EMF, we'll be able to draw the conclusions. Now let's see what exactly is the total EMF of the cell. Now the total EMF of the cell is the potential on the right hand side electrode minus the potential on the left hand side electrode. What is the potential of the right hand side electrode? It's going to be of ferric ferrous electrode. Now what is that potential going to be? E0 plus 0.0591 by N. N is the valency, log concentration of ferric ions by ferrous ions. Now this is just the reverse to what I have done. E0 minus 0.0591 by N log ferrous by ferric can be rewritten as plus. We are taking the plus notation. Okay. So we have this particular value depending upon the concentration, ionic concentration of ferric and ferrous ions. And the left hand side electrode is the saturated calomel electrode. As previously discussed, this is going to have a standard potential of 0.2422 volts, which remains unchanged. Okay. So the overall EMF of the cell is mainly varying with the concentration of ferrous ions and ferric ions. Okay. So this is going to be the deciding criteria to know what are the changes occurring with the E cell of the potentiometric titration. Okay. So we observe that when we are titrating the ferrous solution against the KMnO4 solution, as we set up the whole apparatus again like the previous what you have seen with HCl, okay, but the only difference is when we are taking HCl, we are taking twin hydrone. Here it is not twin hydrone, it is going to be the ferric ferrous electrode which is built. Okay, so we have the ferrous solution taken in 20 volumes in a beaker, and then we fill the burette with KMnO4 and we connect this platinum electrode and the calamine, saturated calomel electrode to the potentiometer with the addition of KMnO4 in 1 ml lots initially. We observe the changes in the values of EMF. Okay, the cell EMF values in this case is going to be different to what we have seen in the previous experiment. Now, in this particular condition, what happens is whenever you are adding KMnO4 to the ferrous solution, we find that there is going to be a decrease in the concentration of ferrous ions, and the added KMnO4 oxidizes the ferrous ions to ferric ions, and therefore there is going to be a continuous increase in the concentration of ferric ions. And so we find that the continuous changes in the values of E cell occur when we are continuously adding KMnO4 in 1 ml lots, where the KMnO4 would start oxidizing the ferrous ions that are present in the solution to ferric. Okay, so the ferrous ammonium sulfate that we are taking 20 ml in the beaker, when added with 1 ml lots of KMnO4 from the burette, we observe that the KMnO4 is oxidizing the ferrous ions to ferric ions. Now this change in the concentration of the ions will bring about the change in the EMF. Okay, the potentials of the ferric ferrous electrodes change. Okay, there's going to be an increase. You can see that whenever the numerator value is increasing, there's going to be increase in the EMF, or you can say the potential of the ferric ferrous electrode, in turn increasing the EMF of the cell. Because this is going to be a standard value, the value changes over here and thus bringing an increase in the value of total EMF of the cell. This is going to be a continuous increase in the value of EMF, because on continuous addition of KMnO4, there is going to be continuous rise in the concentration of ferric ions and continuous decrease in the values of the concentration of ferrous ions. Okay, so this is actually what we observe in the scenario of redox titration between ferrous and potassium permanganate. Okay, now when we follow up the procedure in the similar manner, that is, we are going to prepare a standard ferrous ammonium sulfate solution, and then we standardize the secondary standard solution, which is going to be your KMnO4 solution. I guess the procedures are already discussed in your previous experiment, so I don't need to repeat them. So we are going to prepare a standard ferrous solution, and then we are going to standardize KMnO4 solution, and then followed by estimation. And in estimation, as demonstrated in the previous experiment, we are going to take 20 ml of ferrous solution in along with the platinum electrode, and the other half cell is going to be calomel electrode with saturated KCl solution, and then we place the salt bridge again, connecting both the electrodes to the potentiometer. Okay, we observe the changes in the values of potential difference by adding 1 ml lots of KMnO4 solution from the burette. For every 1 ml of KMnO4 that is added, we observe the change in the values of EMF, and that is recorded in the similar way to what we have done in the previous record, right? So when you observe the values and when you plot the graphs using the cell EMF values obtained at the end of the titration, and then with the volumes against the volumes of KMnO4 added, we observe that there is a continuous increase in the values of EMF. Now, as I told you, there is continuous oxidation of ferrous to ferric occurring. So there is an increase in the overall cell EMF, and this increase suddenly increases in a very drastic manner. So you find the sudden jump in the values of EMF. That's because there is complete oxidation of all the ferrous ions present in the solution to ferric, and no more ferrous ions are present in the solution. So this is going to give you a sudden rise in the values of EMF, and then you find that the values fall in the same slot, like you find this almost standardized values of EMF followed with the addition of KMnO4 after this point of influx. So we get this kind of a standard curve, okay, obtained with the 1 ml lots of KMnO4 added against the cell EMF values taken on the y-axis. Okay, so this is going to be the first trial graph. Similarly, we have, say this is between 9 and 10 ml. Like I have shown you in the previous experiment, there's going to be a continuous 0.2 volume addition near the end point of the reaction to have a close watch where exactly the complete reaction has taken place, to know or to record the exact volume of KMnO4 that is required to oxidize that 20 ml of ferrous solution taken. We are going to have a closer watch with 0.2 ml of KMnO4 added. Okay, so with that we again calculate delta E by delta V values against the volumes of KMnO4 taken in 0.2 ml lots, and then we plot the graph. We are going to again get the point of influx over here again, and from the point of influx that is obtained when we drop a perpendicular line onto the x-axis, this will read out the volume of KMnO4 that has exactly oxidized your 20 volumes of ferrous solution. Okay, then we follow up with the calculation of the normality of the ferrous solution given. So the given sample of ferrous solution will have its concentration calculation by considering the normality equation N2V2 dash is equal to N3V3, where N2 is already known from standardization part, V2 dash is from the volume from the graph, and then V3 we know 20 ml of ferrous solution of sample is taken and N3 is to be found. And then we calculate the amount of ferrous, okay, by considering the N3 into 56. 56 is its gram equivalent weight, that is of ferrous. Ferrous gram equivalent weight is 56. So we get the amount in grams per liter. So this is how we proceed with the principle and procedure of the reaction. Okay, so we'll be able to calculate the amount of ferrous by performing a simple redox titration using the potentiometer. Okay.